So now that we have our values, we have our three groups, what I would recommend doing is pausing this video now and trying the problem on your own. I'll give you a moment to pause the video and you can come back and I'll walk you through how to do the problem. Okay, so the first thing that you're going to want to do is make your sum of squares table. And you'll do this for each group. So again, you'll just, I've already given you the means. You're going to find each score's difference from the mean. You'll square that score and you'll add it up. So for the SSRI, we get 5.2 as our sum of squares. For the placebo, we get 15.2. And for the waitlist, we get 6.8. So jumping back to slide 9, our next step is to find the variance for each group. So we're just going to take the sum of squares for each group and divide it by the degrees of freedom for the sample. So this is how we would do it. We have our variances all lined up on the bottom. We have our sum of squares for SSRI, for example, and we're going to divide that by the degrees of freedom within each group. So within each group, there are 5 people. 5 minus 1 is 4. We're going to do that across each of the groups. Then in order to get your variance within, we just calculated the variance for each group. But to get the variance within, we're going to add all of these up and we're going to divide it by the number of groups. And that is 3. So when we do that, we get 2.267. So that is our variance within. So the next step that we want to do is find the grand mean, which is found by calculating all of the means together and dividing it by the number of groups. And we can also find the degrees of freedom between by subtracting the number of groups by 1. So over here, oh, I already gave you the answer. So we have all of our means lined up over here. We're going to add it up, divide it by 3, and we get 6.6 for our grand mean. Then over here, for our DF between, we have 3 groups minus 1, which equals 2. Then we'll just go on to make our sum of squares table just for the means. So go ahead and make sure you do this right now. All right, and here are the answers. So we get 16.08 as the SS for our grand mean. So then what we'll want to do is find the variance of the distribution of means. So all I need to do here is what we did before to find our variance. We just take this number, which is our sum of squares, and divide it by our degrees of freedom. So we have 3 groups minus 1, which is 2. And here we get an answer of 8.04. So then what we do is we find our variance between. So here, is that wrong? Nope. So then what we do, is to find our variance between. Sorry, I had a brain fart. All we have to do is multiply this number over here by the total number of people in each group. So not the total number of people in the whole study, but in each group there are 5 people. So we multiply 8.04 by 5, which is 40.2. So now that we have our variance within, which we found up here, which is 2.267, and we have our variance between, which is 40.2, we can create our F ratio. So that's going to be 40.2 divided by 2.267, which is going to give us 17.732. So that is our F ratio. Remember that we're not done yet. We still have to calculate out our critical value. So we know that we have an alpha level of 0.01. Our degrees of freedom between is 2. Our degrees of freedom within is going to be 12. We have 15 people total, and we have 3 groups. So 15 minus 3 is 12. So if I go over here to my F table, I'm going to look at the 2 column for our numerator. So that's going to be our DF between. And I'm going to go down to 12 over here for our DF within. And our alpha level is 0.01. So that should give me a critical value of 6.93. Let's see if I'm right. Okay, so now we know that we're comparing our F ratio of 17.732 to our critical value of 6.93. So when we compare them, we can see, what do you think? Okay, we reject our null. Our F ratio is much more extreme than our critical value. Ooh. My goodness. Okay, so that is how we calculate an ANOVA. So remember that we learned that there is a significant difference somewhere in here, but we don't know where that difference is. I don't know if it's the SSRI group that's different than the placebo, or the SSRI group that's different from the wait list, etc. So that's what we've learned. Now I'm going to pause here, and I'm going to show you how to do this on Jamovi. So here is our data. This is how we would enter it. We need to enter it in a series of variables. So we need our independent variable, which is going to be the groups that we make because we have control over those groups. And our dependent variable is going to be people's depression score. We have no control over how people report their depression. So what I would do is I would click Analyses, I would click ANOVA, and we're working on one-way ANOVA. A one-way ANOVA is when we only have one factor. So here our factor is treatment. So here I'm going to put my score in the dependent section and my group in the grouping section. Now you'll see my answers don't line up with what we got. That's because I have don't assume equal. We always want to click assume equal. So that means that we're assuming equal variance within our groups. And as you can see, we get the right answers. So don't forget to toggle this, otherwise you'll get the answers wrong. Okay, and here's what the output looks like. So when we do ANOVAs, we all of a sudden start working with ANOVA tables. So an ANOVA table is what you'll get when Jamovi spits out your analyses. So you'll have all of these different things. And remember, you've calculated all of this. So you have your sum of squares between, you have your sum of squares within, you have your degrees of freedom. In order to get your within variance, remember MS is the same thing as within. You just divide this number by that number. You've done all of this, but this is just so you can familiarize yourself with what an ANOVA table looks like. Okay. So now what we can do is move on to what comes next. When we know that we have a significant difference somewhere, we want to find where that significant difference is. So what we'll do is a couple of different things. Most commonly, we conduct a post hoc test. So a post hoc test shows us where that difference is. It compares, let's say this is for comparing movies, or serotonin, I guess, serotonin release in movies. I'll zoom this in. So it's comparing Mean Girls to Mean Girls, Mean Girls to The Hangover, Mean Girls to Our Planet, Mean Girls to Making a Murderer, Hangover to Mean Girls, all the way down. So what this is telling us is two things. First, it tells us the mean difference between our two comparisons. So for example, the difference between Mean Girl and The Hangover is -10. And then it gives us our p-value. So remember, our alpha is what we're comparing our p-value to. If we have an alpha level of 0.05, we are looking to see whether these p-values are below 0.05. If that is below 0.05, it will be significant. Here we have 0.95, so that means that this comparison is not significant. Here, when we compare The Hangover to Our Planet, for example, we see a p-value of 0.04. 0.04 is lower than our alpha of 0.05, which means this is significant. So that tells us where the significant difference lies that we picked up on with our ANOVA. So that's the most common thing we would do in our post hoc, is a post hoc test. I actually talk about this at the end of the slides, but that's okay. Just note that a post hoc can only be executed after the original ANOVA. So we're not going to look at, we're not going to look to find differences between groups unless we know that there is a difference to look for. That's why we do an ANOVA. If we find an ANOVA that's not significant or we fail to reject the null, we're not going to do any of these other tests. There's just no reason to. I'll talk about a planned comparison in just a moment. I'm going to show you how to do this all by hand, and I'll also show you how to do it on Jamovi in a little bit. So when you do a post hoc, the thing that you need to keep in mind is that it requires something called a chef test. Again, I'm just going to rewind back to some other slides about planned comparisons, but we'll come back to this. I just wanted to bring this up first because this is going to be the most common thing you do. Okay, so again, as we mentioned, an ANOVA only tells us whether at least one group is statistically significant from at least one other group. It just doesn't identify the difference. So one thing we can do is a planned comparison. So there are times where we might think that, or we might expect an answer. So I might expect that my SSRI group will be different from my placebo group. Here we're still using this Mean Girls example, sorry. Oh, I fixed it, but didn't delete the slide. All right. So again, we're pre-identifying the groups that we want to compare, and we do this first. Here are the steps that we need to do for a planned comparison. So you'll see that a lot of the steps are actually the same. So here are just our means. We find our variance within the same way, and our variance between only includes two groups. Here we'll go on to our grand mean, which is calculated the same way, and we'll go on to calculate our variance between. So we're going to end up subtracting our mean 1 from the grand mean, finding that squared value, and multiplying by the number of people in each group. And we're going to do that across both groups, and we'll ultimately get an answer of 44.1. Again, our DF between is going to be calculated in the exact same way. So the number of groups minus 1. And same with our variance between, or our MS between. So we're just going to divide this number by that number. When it's written out this way, I think it can be actually a little bit more confusing, but I promise you, if you go through all of the steps that we went through when we were comparing 3 groups, it'll come out the exact same way. So here, when we find our F ratio, we find 2.3. We're going to compare that to our critical value still, which is 6.93. And because this is not more extreme, we fail to reject the null. But what happens when we do multiple planned comparisons? We can think back to multiple independent t-tests, and this means that we increase our likelihood of type 1 error. Now we can do multiple planned comparisons, but that just means that we need to cover our butts a little bit and establish a correction. So here we establish a Bonferroni correction. So that is where you divide your significance level by the number of planned comparisons. So for example, if I want to compare the SSRI group to the placebo group and the SSRI group to the waitlist, that means that I would be doing 2 planned comparisons. And I would divide my alpha, 0.01, by 2. So this makes my significance level smaller and makes it more difficult for me to find a significant difference. So when we do a correction, it makes it harder for us to say that there is something to be observed. Now we get to our post-hoc comparisons again. And remember, this tends to be more common. We do this only after our original ANOVA. And we do the same, it's the same exact process as a planned comparison. But the difference is that instead of doing a Bonferroni correction, we would do a Sheff test. So instead of dividing the alpha level, we're dividing our actual F statistic. So we would divide our F statistic by the DF between. So it's going to look completely identical, except one more added step. And we're still going to get the same result here because we're comparing it to the same critical value. All right, folks, that is my lesson for you today on ANOVAs. Your quiz is up. Please go take your quiz. If you have any questions at all, please do not hesitate to email me. Have a good day.